So this speaker is Michael Figurnov, who will tell us about our recently accepted paper to CPR conference on computer vision and pattern recognition. And this is joint work with several guys from Google, in particular Maxwell Collins, Yukun Zhu, Li Zhang, Jonathan Kwang, right? Then with us, Michael is researcher in the National Lab in the Faculty of Computer Science, High School of Economics, and also Russell Akhudinov, who was at that time, or maybe is still professor in Carnegie Mellon, but is now also heading Apple AI department. So actually we say that this is a joint work of Yandex, Google, Apple, and High School of Economics.
Except that Apple did not do much for this. Okay. So, all right. Thank you for the introduction. So, yeah, this is the work I mostly did during my summer internship at Google Seattle this summer. So it was recently accepted. Last week I got the news that it was accepted to CVPR 2017. So, yeah. Let's start. In this talk, I will talk about convolutional neural networks. We all know that they are super powerful. They are like one of the most successful deep learning approaches. But the problem is that you get this huge accuracy by the cost of having very, very large computational cost. So if you would like to apply a network like Inception or ResNet to a small resolution image, you would get billions of operations. If you want to apply it to a full HD image, you will get trillions of operations. That's way too expensive for most applications. So I'm arguing that the reason why they are so costly is because they apply the same amount of computation to every pixel of every image. So if you consider the images on the right of my cat, you will see that, for example, here you actually don't want to process the whole image. Maybe you just want to look here, right? To understand that it's a cat. And here it's even more pronounced. Maybe you just want to look, for example, at the head of the cat and not process every...
You're clicking his pointer.
Yeah, okay. So maybe you just want to process subregions like this using a network, but it's just impossible with the current neural networks we have. They use the same amount of computation everywhere. And the second downside of the same problem is that we don't get any introspection about the results we get from the network. We can't understand why it made the answer it gave us. So the biologically inspired solution, which was discussed in computer vision and machine learning community for a while, is attention, which I will define as varying the amount of computation between images or regions of an image. However, up until now, it wasn't very successful or widely used for a number of reasons, which I will describe next. So, one of the class of approaches to attention is glimpse-based attention, which I define as attention which just processes a sub-region of the image. So, probably the most well-known approach to this is spatial transformer networks, which works like this. We take the image, we process it with a fast network, which gives us the location of a box which we want to extract from the image. We extract this box and process just this box and not the whole image. And dynamic capacity networks is somewhat similar. We process the whole image using a fast network, which gives us some coarse features, which are not very high quality, but very cheap to obtain. Then we find the most uncertain features using some heuristic, and then we reprocess these features at these positions using a more accurate network. So the advantages are that you get this guidance of spatial guidance of the computation. So you don't process the whole image, but instead you process some part of the image more than others. And people have tested this on cluttered problem, where you have, for example, like this. You have a digit, but you also have some sort of meaningless parts of digits, and you want to classify the digits, for example. And this sort of attention improves your results on these problems. And you get the introspection just as a computation map. However, there are big downsides. First of all, they use the same amount of computation for every image. It might be not super obvious, but in spatial transformer networks, what is happening is that we always resample this box at the same resolution. So essentially, this network V, which follows from here, always has the same amount of computation. And for dynamic capacity networks, it always uses the same number of the same number of patches is always processed using the accurate network. So it's, again, the same amount of computation every time. Even worse approach is that it's very problem specific. Let's say that we actually want to process, to solve segmentation problem. It's very unclear how you would apply something like spatial transformer networks to segmentation problem, because you actually want to process the whole image in order to get the output for every pixel. And the third problem is that there is a lot of engineering involved. You have to decide how you will construct this localization net and spatial transformer networks, or how you will get the heuristic for choosing the positions which you process for more time in dynamic capacity networks. So it requires usually problem-specific heuristics. The second class of attention methods, which is probably the most well-known, is soft attention, and it works in the following way. We process the image through a convolutional neural network. We obtain a stack of feature maps. Then we predict a weight for every position in this feature map, for each spatial position, all right? So this weight should sum to 1. Then we just take the weighted average of the features using these weights, right? So it may look like this, these weight maps, right? So you usually do this when you want to get several feature vectors for one image. For example, when you want to do image to text. For every word, you might want to focus on different things in the image, right? So it makes sense for this problem, I guess. And it gives you a nice introspection. For example, here the method says that it's a large white bird standing in the forest, whereas it's actually a pair of giraffes. But you might say that a pair of giraffes, which is highlighted, actually looks like a large white bird, maybe. It also seems to give improved accuracy. However, the downsides are that there are no computational gains, because you first have to process the whole image using the whole network, so obviously you can't get any speed up. And it's obviously problem-specific, because you get rid of the spatial dimension. You take the weighted average across the spatial dimension. Again, imagine that we want to apply this to object detection or image segmentation, where we actually care about the spatial locality of things. All right? And the final class of methods is hard attention, which I will simply define as attention methods which use reinforcement learning to train the attention policy. And the last method on this, maybe the second to the last, is dynamic deep neural networks, which works as follows. We have input features N1. We have a reinforcement learning agent here, Q, which looks at the features N1 and decides which path you should take next in the network. All right, so it's like a binary decision, whether you go left or right. And you can train this using reinforcement learning techniques. And these guys used Q-learning. So deep Q-learning for attention, essentially. It obviously gives you adaptivity of computation, right? Because you can choose these branches to have different computational cost. For example, in this case, N2 is another convolutional network, and D is a discriminator, so this is basically exit path from the network. It is also problem agnostic, because you can use any reward function for your reinforcement learning agent, right? This is the essence of reinforcement learning. However, the problems are that you have to engineer a lot for this. For example, here you see the two options they considered for putting these Q-learning agents inside the network. So you can structure it like this, so those are like exit paths inside the network, and those are two alternative branches, where this, I think, is a fast network, and this is a slow network, okay? The additional problem is that it's hard to scale this to large models and large data sets, because reinforcement learning leads to noisy gradients, so it's not very easy to make it work for huge networks. Yes?
Well, I think that this thing is problem-agnostic and the previous one is problem-specific. What's the difference in this matter?
The difference here is that when we talked about soft attention, it when you have this soft attention module, it gets rid of the spatial dimension in your network, right? So this means that after that, you can only reason about the whole image, not about different parts of this image. Whereas in these dynamic deep neural networks, you still get the whole stack of feature maps, and you can still process it in any way you want, and you can use any reward function for training of this policy.
But we could imagine soft attention model where we do not get rid of spatial dimension, actually. We can start soft attention map and then we return back to the image, look at it again and again.
Sorry, I guess I don't follow you. What do you mean?
Or maybe I didn't understand your argument about getting rid of spatial dimension. What did you mean?
I mean that we take these weights and we
Right.
take a weighted average of the feature map using these weights. So we squeeze these spatial dimensions. Instead of 3D tensor, we get 1D vector.
Why is it important? Why do you get?
I guess it's okay. It's very hard to make this convincing argument. In my experiments, I couldn't make it work without that. So unless you do this squeezing, you don't get you get simply uniform maps all the time.
I mean, why squeezing is bad or
Oh, all right. Suppose you want to insert these attention modules after every layer. Okay, you just can't do it after the first one, right? Because all of a sudden you don't have the spatial dimensions anymore.
Okay, thank you.
So, in this talk, I will talk about the methods we propose, which is called spatially adaptive computation time for residual networks. And the way to think about it is a drop-in replacement for residual network, which has attention built in. So it's not an external thing to the residual network, it's like part of the network. And it has several advantages, which are, I think, very useful for real-world applications. So first of all, it's problem-agnostic. We easily used it for image classification and for object detection. So this is object detection results. And these results are from a large-scale COCO dataset. So I think it would be pretty hard to scale the previous methods to these big datasets. And also this is for ResNet 101, which is pretty much the state-of-the-art computer vision architecture at this moment. It adapts the computation spatially. And what I mean by this is that here we see a computation time map, and in every pixel there is a value. I'm not sure if everyone can see it, but here there's a color bar. And this number means the number of residual units, which is the basic building block of ResNet, which is executed for this pixel, right? So the blue ones get something like 6 residual units, and the green ones get something like 24. So it clearly learns to allocate the computation to the positions which require this computation, which are object-like. And this also gives you nice introspection results, because here there are some kites, you probably can see it, but there are some kites which were not detected. But you can see that there is a blob of Pandur cost computation time somewhere around these people. Okay? So this means that the network actually noticed them, but then decided not to output these predictions because probably the confidence was too low. Okay? So you can understand what's going on. And also you can see a blob of computation time here around the wave, which means that it thought for a while that maybe a wave is some sort of an object, but then decided that it's not an object.
Are there any, can you share some story when you introspected the model and then changed something? I'm not exactly sure how to use this intuition, but
I mean, the way to use it would be that, let me think. So, for example, let's say that we want to diagnose some thing in medical images, and we actually, usually the doctor does not care that much about the actual answer, but the doctor wants to know why the model thought that the patient has a disease, right? Then the computation time map might give him the positions where he has to look at in order to make the diagnosis.
So there's a hypothesis that ponder cost maps are actually correspond to uncertainty of algorithm.
Yeah. So, but anyways, introspection is useful if you want to, solve new problems. And here we just applied this to existing problems. So, yeah, it wasn't too much of a help for our purposes. So the downsides is that you have to implement a custom convolutional layer if you want to get speedups from this method. And there's also some engineering decisions you have to make in order to make it work, but I would argue that they're fairly minor compared to what is necessary for example, the previous method I have described. So we will proceed as follows. First, I will describe adaptive computation time for recurrent neural networks, which is a method proposed by Alex Graves about a year ago, which is a method to choose the number of iterations to execute in recurrent neural networks. Then I will explain how we can adapt this to residual networks, and this will give us a method which chooses the number of residual units for an image. So it will be the same for all spatial positions, but it will be different across images. And then I will explain how we can make this spatially adaptive. So for every spatial position, we will choose its own number of residual units. Okay, this will be the final method. Let's consider two examples of a recurrent neural network. So a recurrent neural network processes an input for n iterations somehow. So we have an input, we map it to a state x1, and then we apply the same function f every time to get a sequence of states, right? So we assume that we don't get any inputs past the first attempt step. So we go on. And then at the end, I will, again for simplicity, say that the output is just the last state of the network, okay? So the question is, what if we wanted the network itself to decide on the number n? So we may assume that some objects are easy, some objects are hard, so it makes sense to let the network itself decide how large n it wants to use, right? So this is exactly what adaptive computation time for a recurrent neural network gives us. So in addition to state, we will now have a halting score, which is a number between 0 and 1, and we will obtain it just as a sigmoid of a linear function from the state. Okay, so we'll take the state, pass it through a linear function, apply sigmoid, and get a number between 0 and 1, which we will call halting score. We will keep track of cumulative halting score, so sum of all previous halting scores. And now the output will not be just the last state, it will be a weighted sum of states. Okay? So we will continue. So now cumulative halting score is 0.3, and the output is weighted sum of x1 and x2. We continue, and at some point we see that the cumulative halting score exceeds 1. And this is our criteria for stopping. As soon as it happens, we do not compute any more iterations. So here we will not compute x5 and x6, and we only execute n equals 4 iterations in this case. But this was decided by the network itself because it outputted these halting scores. Okay?
Shouldn't we add like 0.1 times x4?
Yeah, so there are a few things missing. So first thing is that we actually need to compare with 1 minus epsilon, because otherwise we wouldn't be able to stop after just one iteration, because the output of sigmoid is between 0 and 1, so it cannot exceed 1 after just one iteration. So just as a hack to allow it to work, to stop after one iteration, we compare with this. So epsilon might be something like 0.01. The second thing is that we have to add something else to x4 times something to the output. And the most natural choice is choose a number such that all these weights would sum to 1, right? So that it would be a proper weighted average. And we define a remainder r, which is just 1 minus sum of all previous halting scores. So this is exactly this remainder that we have to add, right? So now we see that the output is a weighted average of the computed states. Okay? So this is the full description of how to run this algorithm. but we still don't understand how to train it. Let's discuss that. So ideally, we would like to optimize the original loss function L, which could be like anything, like probably cross entropy of some sort, plus constant tau, regularization constant tau, times the number of iterations n. What's the problem here? If we would attempt to optimize this using graded descent, the gradients would be useless of this part with respect to the parameters of the model, because n is piecewise constant with respect to the halting scores. If we change the halting scores a bit, the number of iterations n does not change, right? So the gradients are 0 almost everywhere, which means that the graded descent would not work here. So now is the main hack which is used in this paper, which is that we use a remainder r, which is this, 1 minus sum of all previous halting scores. We notice that it's linear with respect to the halting scores, and it's also always between 0 and 1, right? Because it's like the... Yep.
I'm sorry, why do we need this regularized in the first place?
The reason for that is that otherwise it would probably always attempt to use as much computation as possible. And we actually want to make it adaptive. So it's for this, yeah, so this would tell the network that we would like the number of iterations to be smaller, if possible. Okay, so we will introduce Panzer-Cost rho, which is the number of iterations n plus the remainder r, which is an upper bound for n, because the remainder is between 0 and 1, right? So we will say that n is simply a constant, so we will use something like stop gradient, which means that it will not take part in calculation of gradients. So now our loss function will be like this. It will be original loss function plus regularization constant tau times Panzer-Cost. Okay? Why does it work? When we minimize rho, we actually maximize this part, right? Sum of all previous halting scores. What this means is that we try to stop the model earlier if that's possible. Okay? Does anyone see what causes the halting scores to decrease? Because here we only say that it's increasing.
The integer n?
No, it's called... Yeah, I mean, in a way, yeah. The original loss function is probably lowest when... so here, n would probably... the original loss function would be lowest when this number is as high as possible, which is also the remainder, right? So the original loss function usually pushes the remainder to be as high as possible, which again pushes the halting scores to be low in the previous iterations. So because of this balance, you get some sort of interesting learning dynamic. Where because if we would not have this other force, what would happen is that the Panzer-Cost would just go to the lowest possible value, right? And then it would get stuck there.
So you want to say that training error is small when we propagate the information further on, right?
Usually, yes. Not always. But in most cases, yes. Okay, now for the residual networks. So residual networks are, I guess at this point, they're not state-of-the-art architecture, but they're the basis for state-of-the-art computer vision architectures. In 2015, they were a major success. They took first places in ImageNet and COCO competitions. Yeah, so they gained a lot of attention because they have very simple structure and they seem to generalize across a lot of problems. So how do they work? Let's say that we have an input image, which will be 224 by 224 RGB image. So there are 3 channels. First, we have a convolution and pooling layers, which are the standard thing in all convolutional networks. And then we have the part which is novel in residual networks. Those are the residual units. So the residual unit is a function of this form, which is input plus some other function applied to the input. Okay, so it computes the residual. In case of residual networks, this function f is a sequence of 3 convolutional layers. So the residual units in residual network are structured like this. They are structured in blocks. So, and I will define block as a sequence of residual units which have the same output sizes. So all these 3 residual units have these output sizes. So there is some magical number of residual units in each block. I'm not really sure how it was designed, but yeah. So the block 3 is the biggest one for some reason. So we have 4 blocks in total. And in the end, we have a global average pooling. So it gets rid of the spatial dimension altogether. And then there is a fully connected layer which gives you the logits of probabilities for classes. So this is a residual network for classification. As with all convolutional networks, you can use it for other problems probably by replacing this part with something else.
And if you apply this architecture to the images in different resolution, what will happen?
It is fully convolutional, so it can be applied to any input resolution.
So the only change will be in this pooling layer, global pooling, right?
Yes. I mean, it's global, so it always gets rid of the spatial dimensions.
Right.
Yes.
So we may, before this global pooling layer, we can end up with a different spatial resolution.
Yes.
Mm-hmm.
So all of these values will be, like the spatial dimensions will be different if you pass a different image with different resolution. Yes, but it's possible. So it will actually be useful for us when we talk about object detection, because when we work with detection objects, we have to work with high-res images with different resolutions. Okay. So why did we think that residual networks can be useful for us? The reason for that is a very nice paper called Deep Networks with Stochastic Depth, which makes the following argument. We can drop random subsets of residual units during training. So it looks like this. So the gray ones are deactivated, which means that we will simply not compute the residual in these layers, and they will be like passed through layers. They will not change anything in the input. And the motivation for that was a regularization effect and acceleration of training. Because we have to pass the image through less layers, we can make training faster. But what we noticed in this is that this means that representations are interchangeable in the network, right? Because the input, for example, to this residual unit might not be just the previous one, but for example, this residual unit, right? So this means that the residual units, their activations are basically in the same space. You can swap them in and out, okay? So it's very hard to make this proper mathematical argument, but the fact that residual networks with stochastic depth work makes it a solid empirical basis for trying this out. Okay, and why the interchangeability was important to us is because if we want to apply adaptive computation time, we have to take a weighted average of residual unit activations, right, of their outputs. And this still needs to make sense. It probably wouldn't be the case if we did the same for a network without residual connections. So the weighted average would not make much sense, and the network would not train very well. So we applied adaptive computation time for residual networks in the following way. In every block, we use this adaptive computation time mechanism. Okay? And then this mechanism tells us when to stop in every block. And because of how it works, for example, input for the block 3 would be a weighted average of these 2 residual units. The input to block 4 would be a weighted average of these residual units. So probably the most uncertain part was whether it would work, because taking weighted average of activations of convolutional networks is not very, I think people do. I don't think people did this before.
Have you observed the distribution of residuals Maybe the answer is that usually when it weighted, most of the time it's 1.8 multiplied in a couple of just smaller activations. Like maybe that's the case why weighted average is representative.
It didn't. It seemed like this. It definitely took average across at least several layers, so it wasn't like a very peaky distribution. So yeah, that's all I can say. I did not investigate it too much. So let's talk about how it works in a bit more detail. So it's very similar to adaptive computation time for a recurrent neural network, with two major differences. The first one is that the weights are now not shared. So they are different for different layers, right? Because it's a residual network and not a recurrent network. And the same is true for the halting score functions. They are also different. The second difference is that x's, the outputs of residual units, are now 3D tensors. Okay? So height, width, and number of channels. They are not vectors. So one thing we had to decide is how to compute the halting scores in this case. And we actually used the simplest possible thing, which is just take a global average pooling of the axis and then pass it through a linear function and a sigmoid. So it's essentially a single layer network. And surprisingly, this seemed to work even better than using a deeper model here. So, yeah. Probably the reason for that is that because we train all of this end-to-end, what we see is that there are some sort of features here which are define how much we want to compute, whether we want to continue computing. So we don't need much more than a linear function here. So that's my explanation.
And pooling, is it performed with respect to spatial resolution?
Yes, just the spatial resolutions. All right. So, as previously, we will stop as soon as the cumulative halting score exceeds 1. Nothing has changed here. And the output will be a weighted average of the computed feature maps. Then we apply it to all k blocks, where k equals 4 in our case. And we simply sum up the boundary costs from different blocks. Okay? Any questions so far?
So, what's the size of the halting scores tensor? Is it just batch size?
Yes, it's just a single scalar for every object.
Okay.
So just as it's shown here.
Okay.
And how to train weights of the later layers? Because in many examples, the network doesn't compute features of the later residual layers, and because the halting score exceeds 1 like this.
Yeah, I will talk about this in 10 minutes.
Okay.
So this was definitely an issue with training this model. So surprisingly, adaptive computation time is a more general model than residual network. So the reason for that is that if we assume that, for example, here the halting scores will be 0 for all objects, and here it will be something close to 1 for all objects, the result will be simply a block which always gives you x4 with coefficient 1. So it's exactly a block of 4 residual units, right? So because of that, we can say that adaptive computation time results in a strictly more general than residual network. So we can always, in principle, recover the original ResNet if we want to, probably with less layers in it.
Well,
Yes.
technically speaking, in order to say that it is strictly more general, you have to prove that plain residual networks can't represent the adaptive ones. So I wouldn't make such bold claims.
Well, I mean, residual networks cannot stop their computation.
Well, but they still can represent the same thing in a different way.
That depends on what you call more general.
Yeah.
Yes.
I mean, in principle, I agree that I would not expect attention models to significantly outperform the models without any sort of attention, because I agree that that a convolutional network can learn a sort of attention model itself. But if you actually say that your attention, the goal of your attention is to save computation, then all of a sudden the fact that a convolutional network learned an attention model inside of itself does not help you much. You cannot use it to save any computation.
Why do we use weighted average instead of just last activations? Same.
So you mean why can't we use just x4 here? So the reason for this is that the halting scores are pushed up by when we want to minimize the plunger cost. But this part, the weighted average, is the only thing which pushes the halting scores down, which means that we want to compute the compute for longer period of time. So unless we have this weighted average, we would always obtain a model which uses just one residual unit in every block. So it's not very, very satisfying answer, but
And you mean the first layer in the block? Always using the first layer?
yes, because the plunger cost penalty would always say that you should use as few layers as possible. Right?
But we do have data term, actually.
Yes, but
Probably we could not optimize with respect to it
right.
if we avoided this averaging. So this is the main reason for averaging. In order to be able to transmit probabilistic mass from the first layers to the last ones.
Okay.
If we use just a single layer, we wouldn't be able to do this.
Yeah, so you can say that it makes the data term dependent on the halting scores in differentiable manner.
Mhm.
Let's put it this way. So, yeah, relationship between the models. Now, spatially adaptive computation time. This is the final step. Now we make this spatially adaptive. And the way we do this is we just use adaptive computation time mechanism in every spatial position. So what this means is, initially we say that we compute the values in every spatial position, and we emit a halting score for every spatial position, right? As soon as the cumulative halting score exceeds 1, we mark the position as inactive, and we don't want to compute the values in these positions anymore, right? So, just as previously, for example, the value here will be a weighted average of the values in these positions which were computed, right? So the same adaptive computation time mechanism in every spatial position. So there are two things which I want to explain about this model. The first thing is how we actually compute the halting scores, and the second thing is how we implement these residual units with active and inactive positions. All right? Any questions about this image? Okay. We will define the plunger cost as simply the average plunger cost across all positions, with the reasoning that if the plunger costs in all positions are equal, we want to recover adaptive computation time mechanism. Okay, so because of that, we just take an average. So for halting scores, we do the following. We will have two branches. The bottom branch is exactly what we had for adaptive computation time. So first we have global average pooling, and then we have a fully connected layer which gives you just one value for an object. And we also have a second branch which is a 3x3 convolution, which gives you a map of halting scores. And then you take a sum of these two and pass it through the sigmoid. So the reason for having the bottom branch is that it allows you to obtain strict generalization of adaptive computation time. Because if you say that the top branch weights are 0, you simply have this, which is exactly what you have in adaptive computation time. Your halting scores map will have the same values in every position, so you will either hold or continue in all the positions, right? So you don't have any sort of spatial adaptivity. The more practical reason was that actually it made training much simpler. So having bottom branch somehow helps a lot. What are the other advantages? one advantage is that this architecture is fully convolutional, which means that the spatial size of the output is the same as the spatial size of the input, which means that you can apply it for images of any resolution. So there is no limit on the resolution. If you can apply residual network to it, you can also apply spatial adaptive computation time. And finally, it's very cheap to compute. Its computational cost is on order of 1 or 2% of the computational cost of residual unit. So it's the overhead is not very large. And because of this interesting design choice, it's a strict superset of adaptive computation time, and therefore of residual networks. So, yeah, I'm not sure how practically useful this result is, but it's good to have this result. Okay, now let's talk about implementing a residual unit with active and inactive positions. So what's the issue here? The issue is that you actually want to know the value in inactive positions, because an active position, for example this one, might have inactive neighbors, right? So let's say that this position is active and we want to compute the convolution in this position, right? Then we want to know the values in all of these 9 positions. Some of them are maybe inactive, okay? So this means that you have to somehow say what is the value in inactive positions. Luckily for residual networks, you have a very simple solution. You just say that the value of residual f is 0, okay? Which is equivalent to just copying the value for the inactive positions forward. You don't change it at all, you just copy it forward. So I'm not sure how we would do this if it wouldn't be a residual network. It would be very hard to come up with a good scheme for imputing these values. Right. And for the active positions, we can just compute the residual unit. So the naive way to implement this would be to just multiply the residual function f by the active mask, the mask of active positions. Okay? So you just compute everything, and then you compute it by this mask, binary mask. Obviously, this would not give you any speedup. So it's easy to implement, but not useful for gaining real-world speedups. The way to obtain real-world speedups is by using perforated convolutional layer, which is something we presented at NIPS this year, the previous year. And perforated convolutional layer is a way to compute outputs of a convolutional layer in a subset of spatial positions. So it works in the following way. On the right you see the convolution by reduction to matrix multiplication, which is actually still pretty popular way to implement convolution. And the way it works is by going through the image and extracting patches for every position. Okay? You take every patch and you put it into a row of a data matrix. It's pretty easy to see that in this case the convolution is just equivalent to multiplying this data matrix by a kernel which was reshaped in some way. The reason for that is convolution is essentially a dot product of patches from the input tensor with subtensors of the same size, which are the convolutional kernels. So those will be the different columns in this matrix K. Okay? And then the output is the output of the convolution, which you just then have to reshape it into the proper size. So what we realized was that you can do this in a subset of positions. You don't have to do it for every position. You can instead choose arbitrary mask in which you want to compute it. And this will give you the results of the convolution in the subset of positions. So the result will be exact, but only in a subset of positions. Because this can be reduced to matrix multiplication, we observed very good speedups, about 80% of the theoretical speedups. And the main issue we had was that we could not choose these perforation masks dynamically. We could not come up with a good learning scheme for those, right? Because it's a binary problem. You have to somehow optimize over this huge dimensional Boolean cube, so it's not very easy to do. What spatial adaptive computation time gives us is a way to choose perforation mask, because it's just active mask positions in this case. So essentially what we have is a way to learn these binary masks using end-to-end differentiable and deterministic procedure, which I think is a pretty unique thing. So at the beginning I wasn't sure this was possible at all, because you would expect that you would need some sort of stochasticity if you want to optimize over binary things. Okay, so this is perforated convolutional layer. Let's talk a bit about training details. So we have found that we can use the same hyperparameters for the original ResNet, for adaptive computation time model and spatial adaptive computation time model. So I think that this is a pretty good sign, because usually when you change something about your model, you have to retune all the hyperparameters, and surprisingly we could skip that when we used adaptive computation time. However, there was a big problem, which is dead residual units problem. What happens is that suppose the last units in a block are rarely used. So the procedure is fully deterministic. So if they're rarely used, you don't have some sort of random variable which might flip on flips that we will use these layers. They are rarely used, or maybe never used. What this means is that their parameters become obsolete. They become not so good, and they do not contribute much towards solving the problem that we have. Okay. And then the Pandro cost penalty that we have says that we should never use these layers because they are useless. Okay, we would gain more from reducing Pandro cost than gain from, from the using those and reducing the loss function. So we have found that two solutions are helpful with this. One is that you should initialize the halting score biases with negative values. So then the sigmoid of this negative value is very small, and what this means is that we use all the residual units initially. Okay? And the second thing is that we initialize the network weights with pre-trained residual network instead of random initialization. The non-convenient thing that we did is that instead of fine-tuning, we actually used the learning rate schedule as if we trained from scratch. So this good initial point was lost very, very quickly, but the halting scores learns again some useful training signal early on. So because of that, the whole training procedure was more stable. Yes?
Can you just add loss of your whole problem to each layer, just to make each layer like training to the result?
So one thing that I've tried was flip a coin, and so with probability 0.5, use the original network, which is just use all the residual units. So it did not seem to work very well. I'm not sure why.
I think it may make sense to use x's from each output and put them into the loss. Use the average of the loss.
So this would result in a polynomial cost, because you have to consider all combinations of the or do you mean just sample how many layers to use in every block?
Why do you say polynomial cost? You have like 10 residual units,
Yeah.
and you can put the output of the 9th one and of 10th one and 8th one, etc. into the loss and just sum up all the losses.
No, you can do this because you have. So for example, you're saying that we can take first, second, or third residual unit from here, but we also have the whole network. We have 3 blocks ahead of it. So, yeah.
Don't you try randomly mix the order of layers in each block? Something like stochastic depth.
No, we haven't. So I think it might work. So actually, I think that what should work is tying the weights of some of the residual units in each block. So for example, say that the first 2 or 3 of them have different weights, and fourth and so on have shared weights. This should more or less solve the dead residual units problem. And the reason we did not do that is because we actually wanted to be able to compare fairly with original ResNet. So we just wanted to use the same architecture. And this would be a different model.
The fact that you initialize your network with a already pre-trained residual network and then use big learning rates seems kind of wasteful. Have you tried just increasing the weights of residual networks and fine-tuning only the HT part?
Yeah,
Is it possible or
It
not?
doesn't work at all. So we couldn't get any good results from this. It seems like you actually have to retrain everything from scratch. It looks like, so my best explanation is that when you do something like adaptive computation time, you force the model to have the most important features early on in the block. And if you don't have this sort of Pandro cost penalty, the most important features might be anywhere. And then the model, if you suddenly introduce Pandro cost penalty, the model has to learn to swap different layers, which is just impossible using gradient descent. So that's my explanation for this.
And actually, it's a little bit different model because we're using average, weighted average.
Yeah, I would say that this is a slightly different model. I don't think this should contribute too much. I think that so what we saw is that we couldn't find the value of tau of Pandro cost penalty, so such that we would have a middle ground behavior. So let's use, for example, half of the residual units when we did fine tuning. So it wanted to either use everything or nothing. So. Okay, so what are the results? So we trained this model for ImageNet, and then we could visualize the Pandro cost maps for different blocks. So this is, introspection results to just understand what's going on in the network. So we can see that the first block reacts to some low-level features. It definitely, does not understand much about the image as a whole. It just puts a bit more Pandro cost to the positions where something interesting might happen, or just, I don't know, something in the convolutional layers react to something. So it reacts to this grass, it reacts to something here, and it reacts to most of the bird. But we see that as we go through the network, in last blocks, we see a block of Pandro cost around the main object. So it's pretty clear that the model has some sort of understanding of what's going on in this image. And I think the most interesting part is that there is a blob of Pandro cost here. So the highest value is around the head of the bird, which is probably the most discriminative part of this bird. So, interesting thing is that block 2 did not learn anything reasonable, it seems. So,
For this particular picture.
yeah. I don't think it did for others as well. So, yeah.
Have you checked it?
I think so. So this is total Pandro cost. So total Pandro cost is just sum of these images. Okay, so just sum them. Here we go, when we go from left to right and from top to bottom, the average Pandro cost increases in the image. So you can see that, generally speaking, the objects which are smaller are easier for spatial adaptive computation time, which makes sense. And also the highly textured natural objects are harder than the, for example, this boat, which is smaller, does not have a lot of texture. So an interesting story here is that on the top left you have an orange boat, which is designed to be very visible. It's orange. And on the bottom right you see a squirrel, which is designed to be a squirrel on a branch of tree, which is designed to be invisible. So this is the hardest object across the ones we considered. So yeah, in general, if you just visualize the top objects with Pandro cost, most of them will have some sort of complicated texture, which correlates well with what we know about convolutional networks. So the numerical results look like this. We trained adaptive computation time and spatial adaptive computation time, and as a baseline, we trained a residual network which has less residual units, and we have chosen the number of residual units in the following way. We took a trained ACT or SACT model, and we ran the validation set through this model, and we looked at the average number of residual units used in every block. Then we just rounded these values to the nearest integers and trained a model with constant number of residual units per block. So it's like non-adaptive model which has on average the same computational cost. So what we see is that when we test at the same resolution as the training resolution, the spatial adaptive computation time and works roughly the same as the baseline, and adaptive computation time does not seem to work too well. So it definitely works worse than the baseline. So the golden line is, this dot is ResNet 50, this is ResNet 101. And on the x-axis you see floating point operations required to process the average number of floating point operations per image. And on the y-axis you see the validation accuracy, the higher the better. So you definitely want to be somewhere around here. So an interesting thing happens when we increase the test resolution. So actually this is a thing which is done very often for classification problems. You decrease the resolution for training because you want to train as quickly as possible. But for testing you use slightly higher resolution to let the model see more details of the objects. And surprising thing happened when we did this with this model. We saw that spatial adaptive computation time suddenly started working much better than other models. And here, ACT works roughly as well as baseline, maybe slightly worse. So then we started investigating this behavior, and we plotted the accuracy versus resolution for different models. And a very interesting thing appeared. When we increase the resolution past some threshold, the accuracy for all models begins to decrease. And this is pretty reasonable. It does not expect the objects to be that big, right? Mm-hmm. So,
how large were the training samples?
224 by 224.
For every graph.
Yes. And in ImageNet, the images are about 500 by 500 on average, but they might have different resolution.
Okay.
So we saw that the results of spatial computation time deteriorated at a much slower rate than for other models. So our explanation for this is that if we have spatial adaptivity, then the model can somehow compensate for the wrong scale. But that's just a hypothesis.
This is not explanation, this is constatation of fact, actually.
Yeah, maybe. All right. So, armed with this fact, we decided to tackle a problem which requires you to work with high-resolution images. So, and this problem is object detection. So, we used faster RCNN detection pipeline, and I will now briefly describe how it works. So, we have image. We use a residual network to extract features from it, and this is the most computationally expensive part. Then we have a set of feature maps, and the first thing we do is extract region proposals from these feature maps. So just region proposal network just predicts a set of boxes which might contain some objects. It does not tell the class, just the fact that there is something object-like there. So there might be a lot of them, like several hundred of them per image. Then we take every proposal, we extract the region of feature map which corresponds to this proposal, and we run a small network called classifier, which attempts to determine whether this is actually an object and what is the class of this object if it's an object. So that's how faster RCNN briefly works. What we've decided to do is to replace residual network with spatial adaptive computation time mechanism. Okay? So just to check whether actually the method can work for different computer vision problems. So the results look like this. You have probably seen. So I have shown you already one example of such computation time maps, but it seems to hold true for most of the images we saw. We see that it allocates a lot of computation to the objects, and it tends to ignore the background. This seems to be generally true. But there are also computation time blobs around things which are not objects, which also makes sense. So, for example, here you see this blob, which corresponds to just some trees. But if you look at them, you might you see that they're kind of object-like. So the computation time maps are not just object detection saliency map. It also somehow correlates with object-like things in general. So the numerical results are presented here, and what we wanted to obtain is improved flops MAP ratio compared to just using less layers. So this is ResNet 101. It uses 100% of the computational time, and it has MAP of 29.2. So you want to get as high as possible of MAP and very low flops. So the most standard approach to this would be to just use less layers in ResNet. So instead of ResNet 101, you can use ResNet 50. You will get about half of the amount of computation, and you will lose about 3.7 MAP points, which is quite a lot. But if you use spatial depth computation time mechanism, you will have slightly higher number of floating point operations, but you will only have a penalty of 1.6 points MAP. So it's roughly 2 times decrease in this gap. So yeah, you can definitely have the same number of floating point operations here in these two models. You just have to tune tau more carefully. So we didn't do this. Here are some more examples of detection results. You can see pretty much the same thing in most images. You will have blobs of very high Pandra cost around objects. You will get some smaller blobs around things which look kind of like objects. And sometimes you have some unexplainable things, like here it allocates some computation here, which definitely doesn't have any objects, but whatever. So you see it does not just trace this whole line, it just puts computation here for some reason. So we also notice that it allocates the computation equally everywhere if there are a lot of objects in the image, which also makes sense. And finally here, yeah, it's just some food before dinner, I guess, but the most interesting thing here is that there is a fork and there is a blob of computation time around the top of the fork. So maybe try to discern between fork and spoon. I don't know. Okay, we thought that this computation time maps look pretty interesting and decided to check whether we can use it as a basic visual saliency model. So the goal of visual saliency is to predict where humans look at when presented with an image. All right? So the way these data sets are constructed is that people, you wear it's called a hat with the eye tracker, and you're presented with image. And then the eye tracker tracks where you look at. Okay? So CAT 2000 dataset was constructed, I think, by MIT guys, and it has several thousand images which were shown to, I think, 20 or 40 people. And the ground truth saliency is simply the locations people looked at, so it was blurred, and that's the ground truth saliency. So it's essentially a heat map of human eye fixation positions. Right? So a big issue with this dataset is that it has a very strong center bias, probably because people were asked to look at some sort of crosshair because before being shown the image. So like, look here, people looked at this point, and because of that, in most of the images you will see a blob in the center, which does not correspond to anything in the image itself. So it's clearly an artifact of this dataset. So here you can probably see it here. So on this image there is a blob of Pandra cost in the center, which does not correspond to anything.
And is it possible to remove it somehow?
It's tough. I mean, without changing the dataset, probably not.
Well, of course, with changing labeling in dataset, with changing this ground truth saliency.
There are some metrics which penalize models which use central bias in them.
So how large is the dataset again?
It's 2,000 images for training and 2,000 for testing.
Well, that's not that big. You can hire a couple of people on Amazon Mechanical Turk and ask them to get rid of those useless blobs.
Yeah, it will be a bit subjective, I guess.
Or you can just allow your model to slightly modify the output of your own map and like have several parameters and train them.
Yeah, exactly. This is what we did. So what we did was we took the Pandra-Cost maps outputted by our model, and we decided to not train the model on this dataset at all. So we just took the predicted Pandra-Cost maps obtained by the model trained on ImageNet or COCO. Then we blurred this Pandra-Cost map a bit and combined it with a Gaussian put in the center of the image, so it would look like this, okay? And we tuned the parameter, which is the coefficient between Pandra-Cost map and Gaussian. So this is what I mean by post-processing. So,
Michael, but I do not see this correction on second image.
yeah, it's there.
Now then, it seems to be rather weak, weaker than it is needed. No?
Maybe. So
Because I don't see any point in the center of this Pandra-Cost map at all. Although it is definitely present on the ground truth.
So this probably has to do with the metric we used, which is a ranking criteria, which says that the value of predicted value of saliency in the positions where people look at should be higher than in the positions where they don't look at. So essentially, what this Gaussian gives you is that the this background value here is higher than the background value here. Okay. So yeah,
Okay.
the thing about ranking criteria is they sometimes give you this sort of behavior. Epsilon change in the values might result in very big change in the metric.
Okay, good.
So the center baseline achieves 83.4, and our model outperforms it by 1% in something.
Not too impressive, actually.
Yeah. But it still means that there is some sort of useful correlation between Pandra-Cost maps and where people look at. So I will discuss in a couple of slides that we can actually make it better by explicitly training to use these eye fixation positions.
Is there information about what kind of classes are in images in datasets, or that just it supposes that attention is universal for all subsets of objects? I mean, like, you have some, when you trained your model, it has learned some amount of objects that are described by classes, and in saliency dataset, people looking at, like, those two images, for example, are pretty abstract, and the first one has a human in it.
Yeah.
And humans are in, there are humans in some datasets that you
Okay,
learn.
I got good question. So there are 20 classes which are very diverse. So some of them are like random noise, others are like fractals. There are paintings. There are like human activities, like here. So it's a very diverse dataset. Yeah. So maybe.
And no labeling is available. I mean, no class labels.
Well, you can use it, but no one uses these labels, I guess. So they're just the different types of images are put into different folders. You can of course use this as labeling, but
I
nobody.
mean, like, there might be a case that saliency might be applied in a like, if you have hierarchical objects, you have different saliency on like low level features, on high level features, and like you compare across different levels of features. Like, it seems to. Like when you assemble, for example, if you look at some part of human and your algorithm knows, like, have a model of how you should compose a human, like, you know where to jump to see different parts of human from the higher level. But if you have only textures, you only like look into low-level textures around the initial point. Well, it's
Yeah,
just,
I guess this is the same problem we have when both people look at the image and when the model looks at it. I mean, you can argue that people are trained to look at images like this and not like images like this. So both a human and a convolutional network would have pretty much
okay.
the same problems in this regard, let's say. Yeah, but what I want to emphasize here is that, for example, it works reasonably well for paintings, although there were no paintings in ImageNet or COCO. So yeah, it also gives something reasonable for fractals, although there are definitely no fractals in ImageNet and COCO.
And this residual network was trained on image classification problems.
So this one I think is COCO. Yeah, so it was trained for object detection. Or maybe,
Object detection or classification?
sorry, I don't remember. Yeah, we changed it several times when we wrote the paper, so I don't remember which one was in the final one.
But the numbers are pretty much the same for classification.
Yes,
and
but the
detection.
Pondercost maps somehow look a bit different. So, yeah, I don't know. I remember that for classification they were more picky, and for detection they were more spread out. Because when you do detection, you actually want to understand the borders of the image, and when you do classification, you just want to know the class. So it's different. Okay, now to conclude, I think we have shown that we can use adaptive computation time for computer vision, which definitely wasn't obvious at the beginning, and I think that this opens way to a lot of interesting developments, both in theory and in practice. So hopefully this will allow to, amazing new gadgets to be developed or something. Spatial adaptive computation time is the main method we presented, which adapts the number of residual units per spatial position, and it's essentially a drop-in replacement for ResNet. And it looks like we can improve the speed accuracy trade-off using this, especially when we're dealing with high-resolution images. The computation time maps which we obtain from spatial adaptive computation time seems to correlate well with human eye fixation positions, so it's a sort of a weak visual silencing model. And the main message I have in this work is that maybe we should use attention maps which reflect the amount of computation that is necessary to process the part of the image, and not just arbitrary weights as what is done, for example, in soft attention. Okay? Let's talk a bit about the future work. Any questions? Yeah.
Probably it's a question about your paper, the previous one about perforated
Okay.
networks, but when you do the comparisons in terms of, all the comparisons were in terms of flops, right?
Yeah.
It's, okay, they're not empirical.
Yeah.
Just
Okay,
one
but-
question about this table. Was it possible, ResNet, not 50, but maybe 56 to compare the results exactly?
Yes, that would also be possible. Yeah, I just didn't have enough time to finish
It
this.
would be better.
That's true. Unfortunately, this takes a lot of time to compute. It takes several weeks at least. Yes.
But what's happening on practice? I mean, you need to use this matrix multiplication implementation for convolutions, and did you succeed in implementing as efficient as, let's say, using other methods for convolutions and using no salience maps?
So for implementation of this paper, what we used was just the naive implementation where we just multiplied the inactive positions by zeros. So for perforated CNN's paper, we implemented this efficiently, and it actually works. So it's definitely doable, but the implementation was in Cathay, so I did not want to spend too much time porting this to TensorFlow, and I didn't. So.
And what is your expectations on like how would the speed up may be if someone smart will sit down and write a good implementation? So is it like twice faster on test or what?
So I think there might be some. So I would expect something along the lines of the same 80% of theoretical speed up. Maybe 70% because now your masks are dynamic. You can do some of the optimizations you can do when they're static. But I think 70 to 80% should be reasonable. The main problem with that is that the most efficient implementations of convolutions right now are probably QDNN convolutions, which are proprietary. You cannot get access to the source code. So unless you work at NVIDIA, it will require you probably a lot of effort to make as efficient convolution.
Yeah, I mean, you're saying like 80% of the theoretical speed up. But what is your expectation on the theoretical speed up for practical problems? Like, what do you expect the overall?
This is just the this value. So like here it would be twice the theoretical speed up is about 2 times. So it's the ratio between this and this.
Is it accurate to, can we expect that time needed for inference or training can be proportional to flops?
So, I mean, when for perforated CNNs, I have implemented these kernels, and we saw that the empirical speedup is about 80% of the theoretical.
No, I mean like, it's actually like a little bit suggests that flops are like, if you spend some like percent of flops, it means that it's linearly related to total time. Like, I mean, is it the case? I mean, like, it might be less flops, but the computational that required to perform those flops in practice doesn't like scale to the same amount of time.
You mean due to some overheads?
Yeah.
But I think this is exactly what Michael tells, that practical speed up was about 80% of theoretical one, due to these overheads.
Yeah, so I mean, here this would mean that the like in theory it should be about 2 times faster, but in practice maybe it would be 1.7 times faster or something like this. Yeah.
And how those flops are distributed across the network?
Most of them are in block 3 because it's just the biggest one. So,
but if you detail the block 3.
Wait. I understand your question. So, you're talking about this, right? So, essentially, every residual unit in the network has roughly the same computational cost.
Okay.
So, it's just proportional to the bundle cost, essentially.
Yeah. And
And
I will just propose kind of simple scheme, and can you tell me if that makes sense? So I've noticed that, let's say the first layer, what they can do, they are activated when they see some texture, and you basically told us that.
Probably. I mean, that's a post-hoc explanation.
Yeah. So the bundle cost map is not sparse if there are a lot of textures on the picture. So the network kind of has to look at all the image, right? The whole image to understand something.
Okay. Yeah.
And it seems like we're spending a lot of computations at the lower levels when we see kind of details of all the textures, but eventually we will understand that the object is centered and we shouldn't confuse anything for the context, right? I mean, even if the texture around the object is rich, yeah, then the first layers are still looking at it, and it's because of the what's called the resolution they look at is small, and they cannot not. But what if, let's say, you first see a small picture, let's say you downsize your image in 30 times, you process it, and then you kind of sample once more.
So some kind of taking into account global context, right?
Yeah.
Yeah, so I guess this is what we try to achieve when we do, when we have this pathway for halting scores which uses global pooling. It does something similar to this, maybe not exactly. It's a sort of a global context. So I'm talking about
Yes.
about this. So you could imagine doing something more complicated, but this would be, you know, I would say it would be less natural and more complicated to make it work. So we couldn't find a very good way to do something like what you're saying. But I mean, it's generally true that you know, top-down inference is important. So this is just one instance of this.
And can you tell some words about nature of halting scores? We saw that they increased from level to level inside one block.
Okay.
But what time they decrease? What's the nature of this decreasing of halting score?
So
Can be.
halting scores are just functions of the intermediate representations of the network. So they will be different for different objects. And yeah, so the network itself learns to, it's like a, you know, tool for the network to learn, that it can learn to use. So that you cannot say that they will always increase or decrease when you go through the network. It's just...
What is the nature of decreasing?
So you're asking why they decrease
Yes.
at all during training for the same... Okay, I see. So I guess the answer is here. So they decrease because we have modified our loss function to penalize using too many layers. So now we have this boundary cost, which says that we don't want to spend too much time on every image. So we want to hold as soon as possible. Because of that, no, that's increasing of halting scores. So we
Decreasing, I can understand.
Okay, you're asking about decreasing. So for decreasing, what happens is
So
that...
well, this picture says 0, 1, 0, 2, 0, 6, and then 0, 5. Why it so can be?
It is this way. Those are just arbitrary weights between 0 and 1. All of them could be any values. They are not necessarily monatomic.
Because we are dealing with a cumulative halting score, not with
Yes.
a single halting score, but with cumulative. And cumulative halting score, of course, always increases.
Yes, it's just a sum of all of them. So this one is,
But
of course,
the
monatomic.
single y can decrease.
Yes.
I understand. Why can then decrease?
Because the function here is non-linear, so essentially it can, yeah, I mean, all of these functions are non-linear, so there is no monotonicity of any kind. I would answer it this way.
Okay, and when you're, maybe next slide, just here you are trying to decrease the number of layers.
Yes.
But if is it possible the opposite process when the loss function becomes less when you make more layers, because the results much more better when it's not 3 but 4 layers.
Yeah, this is exactly what is happening, and because of this, this term, which is the original loss function,
Yes.
wants your number of iterations n to be large, whereas this term wants it to be low.
Have you ever saw such a result?
Yes. So unless this would be the case, it would always use the least possible number of iterations. But you can see it even visually on these images I've shown you, that it's definitely not the minimal amount. So the minimal would be, I guess, 2. The minimal boundary cost would be 2, but here it's, for example, 3.3. Here it's 18. So it's definitely not using the least possible number.
So for some regions, it is using the maximal possible amount of
Yes.
layers.
For some regions, it wants to use the maximum amount of computation.
And it is known that the more layers are in the block, the more layers are in the residual network, the better. The classification is generally better. This is why the data term, this loss function, if not regularized, tends to increase the number of layers used.
Yes. Okay, any more questions?
No, about the COCO results, please. Yeah. The table with the scores.
This one.
Yeah, this one. Could you please comment on the difference between your implementation and ResNet implementation scores?
Oh, so this implementation is from the original paper. This is the implementation, yeah, the guys at Google had, and it's better. So that's a kind of story.
Another
Well,
random seed maybe.
considerable difference.
There are some slight differences. So one difference is that original ResNet 101 was trained in two stages somehow. First they trained the region proposal network, and then they trained the classifier. In the internal implementation it was trained end-to-end. So this is one cause. They probably also tuned hyperparameters a bit better. So both of these combined resulted in a pretty big improvement of MAP. So, which is why it's not always the case that comparing against the published results is the right thing to do. Sometimes you actually want to compare against the results you obtain with your hyperparameters. Okay, any more questions? Okay. Let's talk about some future things we can do. So, you have probably noticed that there is some unsatisfying mathematical explanation for adaptive computation time mechanism. And right now we're trying to fix that together with Artem and Dmitry. And we're designing a probabilistic model which has similar properties to adaptive computation time. And in like 2 points, the idea is that we take the halting scores and replace them with Bernoulli latent variables. And then they become 0 and 1. There is no this complicated thing about when they're not 0 and 1. And we can say that the puncture cost will now be a prior which penalizes the expected halting time and not some complicated puncture cost which is a heuristic. For training, we can relax this Bernoullis using a concrete distribution. And this allows to use gradient descent to train this model. And of course, this can also be extended to spatial adaptive case to have probabilistic spatial adaptive computation time. So the downside is probably that this model will have noisy gradients. So adaptive computation time was deterministic. This model is stochastic. So maybe it will be slightly harder to train. So we're currently working on it. So for future work, what we can do is do semi-supervised training of halting scores. Right now, the puncture cost is trained without any explicit supervision. Sometimes we might have access to the eye fixation positions. And in the spatial adaptive computation time model, there is a nice way to incorporate this information. The way to do this is to not penalize the puncture cost in the positions where people look at. So we'll have this sort of a term which means that if people looked at this position, the puncture cost will become 0 in this position. So we don't care about it. As a result, we will get a network which is explicitly trained to spend more computation on the positions which people find interesting or important. Okay. Another interesting development would be to make the halting scores conditional. Right now, they only depend on the feature maps, but we can imagine a problem like visual question answering, where we have a question and an image, and we want to answer this question using this image, like how many apples are there in the image? There are 3 apples, and that's what the answer you have to give. And it looks like attention methods are generally useful for visual QA, and maybe what we should do is say that the halting score outputs should be conditioned on the question. What this would mean is that depending on the question, we would spend more or less time on different parts of the image. Like if the question is about apples, we would spend more time on apples. So unlike the attention method which I used right now, this would actually correspond to using different amount of computation in different parts of the image depending on the context. And the final slide I have is video processing. So this is, I think, the ultimate application of all this thing, adaptive computation time technology. So as I told you, it's very expensive to process even a single high-resolution image, like Full HD. But suppose we have a 1 hour long movie of Full HD images, right? It's just too expensive to process right now. So what people do is use some sort of subsampling, like process just 1 frame per second or per minute or something. Maybe we can do better than that. So let's say that we will vary the amount of computation in every frame. We will propagate the context between the frames. So we will pass it here, and if nothing has changed in the view, in the frame, in the scene, we just spend less computation. In this way, we can proceed until something changes, and then the model itself decides to allocate a lot of computation to the new frame, etc. So it's relatively easy to come up with a way to propagate the information between frames. You can just use LSTM, for example. But up until now, there was no good way to adapt the amount of computation in every frame. So it was hard to make this model, trainable. So I think spatial adaptive computation time is a good starting point for these kind of applications.
Am I right that your model is cheaper on the training time than the full percent? Or not? Like on the test time, you surely save some computation, but on the training time, do you also save?
Yes, I mean the model has exactly the same behavior during train and test time.
And will it be the case if you develop the reduced version?
Hard to say. You might save something, but probably not as much as in adaptive computation time during training. For testing, you would probably save roughly the same.
Wait, but you said that in order to train SACT, you actually need to start with already trained network.
Yeah, that's right.
So you will spend strictly more time.
Right.
Well, I mean, it's a common assumption in computer vision that you have an access to a pre-trained model.
Oh, by the way, what about the training time? Like, how much is how long is it compared to the just plain percent model?
Well, because of the implementation we used, it was slightly slower, maybe 20% slower. I don't think it was.
You mean per iteration or with less iterations or time?
Both, because we used the same number of iterations.
Oh, okay.
So why it was slower?
Because you do this sort of masking, which takes a bit of time. So taking weighted average across tensors somehow and masking takes some amount of time, unfortunately. So you can probably optimize all of this, but we didn't spend much time on that.
But like if you used 1 million iterations for both models, obviously they will both take the same time and both will converge. But if you use like few iterations, are they behaving like similarly to each other in terms of time to train the reasonable level?
So the learning curves looked very, very similar for ResNet and for adaptive and computation time and SACT. So that's all I can say.
Do you think it's possible to translate this understanding from the SACT model to some model that uses implicit Laplacian pyramid? So what I'm trying to say is, if we have our attention maps at different resolutions, is there a way maybe to have a higher resolution on demand of the model? If I'm saying that if we have a picture downsampled to some resolution, and our model is able to resolve the uncertainty at this scale, and is it possible maybe to make a model that's able to adaptively go into more detailed parts of an image, like downward, depending on its attention mechanism?
Yeah, I think this should be doable. It sounds very, very similar to just appending the input image to the inputs to blocks. So like halfway through the network, you append a downsampled image. So I don't immediately see why it should help a lot, but it might help a bit.
No, I don't mean like to help the classification accuracy or any other metric, but I mean to maybe save more resources when you have an image not in its highest resolution, but you have pre-computed different resolutions. And in this setup, you use your attention to guide your computation to go into different parts of an image at different resolutions.
Okay, I would say like with all attempts to save the computation depends on the details. So
Yeah.
And the details can be discussed afterwards.
yeah. So thanks. That's it. Yeah. If there are any more questions, feel free to ask.
Maybe just any more general question. It's there is a lot of reasons not to work with the raw image, but to make a special Fourier transfer and work with it. Do you know anybody who works with this Fourier transfer of the image?
I'm not sure. I think I've seen some papers.
Okay. If you will be
Yeah, I'm sure.
so kind to send me later on some such work, I will be grateful.
However, the Fourier transform is a linear operation, so it should not be that hard to learn it from data if it's the right data.
But it's, well, global linear operation. It can be learned, say, using, say, convolutional layers.
So
You need,
That's sure, it's kind of global. I mean, it's not strictly global, but
if this is global Fourier transform, it is global linear transformation. Or you might think of some localized Fourier transform that is also possible, and this, at least in theory, can be learned using some analogs of convolutional kernels.
So there have been papers which which learn the convolutions in Fourier transform, in Fourier domain, and the reason for that was that they tried to obtain invariance to rotation, so that if you rotate your image, you would get the same output after convolutional layer. But yeah, this is
It
very
will be very strange.
yes.
If convolution will be the same after rotation, it won't be.
Well, if it's in Fourier domain, then it's okay. No. Any more questions?
So then let us
Okay.
thank the speaker for very interesting talk. And I would just would like to tell a couple of words as some new conclusion. So you see that this research was done over residual networks architecture, and this is quite interesting since residual architecture is some kind of null architecture in deep learning with these residual connections, and it appears that it possesses several interesting and attractive properties. And it was only due to these residual connections that this spatial adaptive computation time became possible. So this is an interesting example of how changes of classical neural architectures may imply some new insights, some new modifications of deep neural networks themselves.